The group of elements known as the Actinide series is at the very bottom of the periodic table. The actinides share some properties with the transition metals, including high melting and boiling points. However, they are all radioactive, and most are artificial, which makes them unique among all the groups in the periodic table. Although these elements are a sub-series of the transition metals, their group has often been considered separately. The actinide series generally includes the 15 elements from actinium to lawrencium. All actinides heavier than uranium are artificially produced, either in a laboratory or as a byproduct of nuclear reactions. Most of the actinides weren't discovered until the 20th century, when technology allowed scientists to create the environments necessary to produce and detect these elements. All the actinides are radioactive. Uranium and plutonium are probably the best known of the series. They gained worldwide recognition as the key components of the atomic bombs dropped on Japan at the end of World War II, and are still vital for nuclear weapons today. But radioactivity can also be beneficial. The actinides are commonly used in cancer treatments and as an efficient heat and power source. The radioactivity of the actinides can be explained by taking a closer look at the periodic table. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. The actinide series is entirely in period 7, meaning that every atom has 7 electron shells. The electrons in this outermost shell are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. The elements are listed in order of their atomic number, which represents the number of protons in an element's nucleus. In an element's normal or ground state, the number of protons in the nucleus is equal to the number of electrons in the shells. The radioactivity of the actinides stems from the nucleus. This is why applications that use radioactivity are described as nuclear. The elements in the actinide series are some of the heaviest elements in the universe, so they have very high atomic numbers. The nuclei of these atoms are so big that normal atomic forces can't hold them together, and they become unstable. The nucleus releases matter and energy in an attempt to gain stability. When this happens, the atom changes or transmutes into a completely new element in a process called radioactive decay. There are several types of decay, each releasing a different form of radiation. Alpha particles are the most common form of radiation in the actinide series. An alpha particle is the same as a helium nucleus with 2 neutrons and 2 protons. When an element undergoes alpha decay, it turns into a new element with 2 fewer protons. For example, americium-241 has 95 protons and 146 neutrons. It experiences alpha decay and becomes neptunium-237 with 93 protons and 144 neutrons. In this equation, the alpha particle is written as helium. Beta particles are electrons, but they are ejected from the nucleus. Beta decay is more common in radioactive isotopes of lighter elements. A beta particle is formed when a neutron in the nucleus turns into a proton and an electron. The electron leaves the nucleus, and the atom transmutes to the element with 1 more proton. For example, actinium-227 with 89 protons and 148 neutrons undergoes beta decay and turns into thorium-227 with 90 protons and 147 neutrons. The beta particle is written here as an electron. The most familiar type of nuclear decay is fission. In fission, the nucleus of an atom splits into smaller nuclei, and energy is released in the form of gamma rays and subatomic particles such as neutrons. When uranium-235 undergoes fission, there are several different nuclei it can split into. 2 common products are barium and krypton. Fission is the type of radioactivity predominant in nuclear reactors and nuclear weapons. Many of the actinides result from the radioactive decay of other elements. This understanding of radioactivity was what allowed scientists to isolate and identify all the elements in the actinide series.